Okay, welcome to note set number 11. And so we are already into chapter 5. So the reason is that a lot of the first part of this book is pretty much review. So we've been hitting just the novel stuff and kind of re-hitting some of the stuff that you've seen in your signals and systems class just to get us up to speed. Soon we'll be into some brand new stuff that you've not seen. So just as in chapter 4, there's a bunch of stuff in there that you should have seen before, and we're going to just hit the big ideas here. So the things that we're going to see here are the biggest ideas, and you should have seen those before. Okay. So now we're talking about how we use the DTFT for analyzing systems. In the previous note set, we saw how to use it to analyze signals. Somewhat, a little bit anyway. Well, we'll revisit that concept later when we talk about the FFT. But now we want to analyze a system, and we've been talking about the transfer function, we've been talking about the frequency response, how those are related, and this kind of shows where the frequency response comes from, and we'll see it two different ways. So the first way here, we're just going to ask what happens when I put a complex sinusoid into a system, and we're going to hypothesize based on the fact that we really do know the answer to this. We do know that if we put in a complex sinusoid, that same complex sinusoid comes out with a complex number out in front. So notice that, I know it's a function of omega, but we're imagining that this omega is fixed at a specific value. And so we think of this as just a single number. In fact, it's the number picked off the frequency response function at the point where the frequency is equal to whatever it is that we put in. So that's kind of the way to think about that. It looks like we've got a function of two different things there, but in reality, we don't. We've just got a function of one thing because we're imagining omega being fixed at some specific value. Suppose we could put in omega sub 0 if we wanted to. So what we're going to do is start with our difference equation and basically just sub in this for x and this for y. So when we do that, we've got our y values over here. So there's y of n. Here's y of n minus 1, and you can see that when we let n go to n minus 1, the only place that happens is up there, so we get this kind of behavior. And we keep doing that all the way down to the n minus n term. And then the same thing over here, except we don't have the h. Then we do a little bit of algebra. So let me get rid of some of this stuff here. Whoops. Sorry. Oh, my dog just walked into the room. She's wondering what I'm doing up here talking to myself. So if we then do a little bit of algebra, if we pull this common h out, and we pull a common e to the j omega n out, we're left with basically a polynomial kind of an e to the j omega, or 1 over e to the j omega. And we end up with another thing over in brackets there. And so now we're just going to solve for h of omega. And when we do that, we get something that looks like this. So now we see that this is in fact our frequency response, and should look awfully familiar to how we got the z transform version, the transfer function. And if you go back and look at the transfer function in terms of z inverse, you can see that indeed we've just replaced z by e to the j omega, just as we're used to doing. And just like we can get the transfer function by inspection, we can get this frequency response by inspection. So we now have an easy way to go from the difference equation to the transfer function, and the same essentially easy way to go from the difference equation to the frequency response. Okay, on to the next slide. So what we just showed was that if I put in a complex sinusoid, this is what I get out. Well, if I do the same thing for e to the minus j omega, I can use Euler's formula and linearity, and we can actually show that a real sinusoid goes into the system and comes out with the amplitude A modified by the magnitude of the frequency response and the angle theta that the sinusoid went in with modified additively by the angle of the frequency response at omega 0. And here I did put in the sub-zero, which makes it a little clearer. So either of these results basically tells us the same thing. We're seeing that what we're getting here is that the frequency response, up here we're seeing it as a complex thing, and it's multiplying both magnitude and phase all in one package, because it can do that mathematically with the exponential. But when we switch to the cosine form, we need to handle the effect on the amplitude separately from the effect on the phase. But it's basically the same thing, and this is the big idea down here. What this is telling us is that a linear time invariant system basically does two things to a sinusoidal input. It changes the amplitude multiplicatively. So all we have to do is look at the magnitude of the frequency response, and we can see at each frequency whether it's going to boost, leave the same, or cut the amplitude of that sinusoid at that frequency. And it changes the phase additively. So we can look at a phase plot to see, how it affects the phase. And really, this is the big idea. Whenever you're thinking about what a system does in terms of Fourier analysis, we're thinking about what it does to sinusoids. And then Fourier says, hey, the signals that we're interested in analyzing can be thought to be made up of a whole bunch of different sinusoids, all quote unquote added together. And the frequency response just shows us how each one of those frequencies, amplitudes, and phases gets changed. Here's an alternate way to find the frequency response that's a little more general. The previous way we just looked at, we had to kind of hypothesize what the structure was, but we can use properties of the delay property of the DTFT. So we start with our difference equation, and we basically say, all right, take the DTFT of both sides. Since they're equal, we should still have equality. So here we're just showing, symbolically, take the DTFT of that. Now by linearity and the delay property, by linearity we can pass the DTFT through to each term. When we pass it through to here, we just get y of omega. When we pass it through to here, we get, using the delay property, we get an A1 y of omega times e to the minus j omega. And then, so we see the action of the minus 1 all the way down to the action of the minus n in this term. And same thing on the right-hand side. Okay, so then the next step would be to do some algebra. So we've got a common yf term on that side and a common xf, or x of omega term on that side. So we pull each of those out. And then we solve for y. So we take this part and we swing it over to the other side, and we end up with something that looks like that. And so that is how we find the output of the system. So we see that the output is indeed our input DTFT times something. That something has to be the frequency response. We know that's the general structure. We've seen that already. And so now we can just from that deduce that whatever's in the square bracket must be the frequency response, and it's exactly what we saw on the previous. So to try to summarize this big idea, we've got an input e to the j omega n going into an LTI discrete time system. The thing that comes out is that same complex sinusoid whose amplitude and phase has been modified by the frequency response. So that's putting in a single one of these things. Now imagine putting in a continuum linear combination of that, adding up these for all possible frequencies. And when we add up for all possible frequencies, we must add up over the continuum. So instead of summing up at specific frequencies, discrete frequencies, we have to do an integral over the continuum. But it's really no different than just adding up a bunch of these things as functions of time for each individual frequency, and it's weighted by the input signal's DTFT. So that input DTFT acts just like, analogous to a phasor, which you saw in your circuits class, at each individual frequency. And since we added these things up with these weights, we need to add these things up. And so, we're putting in these components individually. We get out this component. Since we added those up, we add those up, and we get our result here. And so we see now that this is really just showing us here that that the output is indeed just the frequency response times the input DTFT. So this tells us how we think about this, what the inverse DTFT is really doing. It's really, when we think about it from the system analysis point of view, it's really just adding up a whole bunch of different components at the input and adding up a whole bunch of components at the output to create these two different signals. So this is just our general result restated here. We've got some system. We can think about x of n going in. We can think about y of n coming out. And we're basically going over into this new domain, modifying it by the system to get this, and then transforming back to get y of n. So that's how we think about it. We don't necessarily always do all of that, but that informs our thinking about how we do this. So the main thing that this informs us about is that this frequency response tells us that its magnitude is going to emphasize some frequencies and de-emphasize other frequencies. And some it might just leave completely untouched. And so as we are trying to understand how a particular system works, or we're trying to design a system to do a particular thing, we don't necessarily do all this math, but we certainly rely on the math telling us what this frequency response is showing us, and we design with our eye on the desired frequency response rather than with an eye on the desired impulse response. So that's kind of the insight that all of this gives us. And so this just summarizes three ways that we can use the frequency response. We didn't really talk about the middle way here, but it's just like using frequency response for a Fourier series for a continuous time. But we did talk about this result, and we did talk about this result. And in each case, we're basically just doing the same thing. It looks like perhaps three different kinds of ideas, but it's really the same idea. The amplitude gets modified and the phase gets modified. So the frequency response modifies both amplitude and phase. We see the same thing happening here. This frequency response is modifying the Fourier series, which is telling us up here what the amplitude and phase is of each sinusoidal component. And then the same thing over here. The magnitude and phase of the input are getting modified by the magnitude and phase of the system, and then the DTFT inverse is just doing something similar to this sum, except it's doing it as an integral. So you should be able to, you should know how to do each one of these three paths. So make sure you understand how each one of these paths works. So here's an illustration of a ideal discrete time low pass filter, and we can't really build one of these. And in fact, if you can prove to yourself that that's impossible. If you tried to take the inverse DTFT of this to find little h of n, the impulse response, you'd find out that it's a sinc function, and that sinc function is infinite in both directions. Infinite duration in both directions, so it's certainly not causal, and it can't even be delayed into being causal. So it's just hopelessly non-causal, I guess is the right way to say that, even though that's not really technical. So here I'm using B for the cutoff frequency of this filter. On the next slide, I kind of screw up and I use B for something else, so don't get too hung up on what B is here. We could change this B here to maybe call it something like capital omega of sub-zero. And then we don't have to fuss with this B on the next slide. So we've got this ideal low-pass filter, and what happens if we apply it to some signal? So here's where I inadvertently used B for something yet again. So B here is in hertz. This is our continuous time Fourier transform in terms of the capital F, which is in units of hertz. I know I hate that. That's the one main thing I don't like about this book, is the choice of things for the frequency variables, but I'm getting over it. Well, I'll never get over it, but I'm okay with it. We'll just move on. So capital F is our frequency in hertz, continuous time frequency in hertz. B is in hertz. It's the largest frequency in our signal. So we know that we can sample, at least theoretically, at the critical sampling rate, the Nyquist rate of 2B. When we do that, we get a DTFT that looks like this. And because we are sampling, critically sampling, that means that this edge is going to show up right at pi. If we actually sampled at a rate higher than 2b, we'd see a little gap here between those two triangles. So I would encourage you to think about that and consider what would happen if we sampled at faster than 2b, and try to draw this diagram for the case where you're sampling faster than 2b. Okay, so let me clear some of that off. But in this case, we're doing critical sampling, and so the x of n going into our discrete time ideal low-pass filter looks like this. And then suppose that our ideal low-pass filter looks like what's on the previous page, and suppose that we pick a cutoff frequency somewhere like that. That was that omega sub-zero that I was talking about on the previous page. So now we're going to multiply this times that, and if you remember, not only did it stop and pass there, but it also does it for all of the replicas as well. So when we do that, we multiply those together, we get something that looks like this. And now we can see the action of that low-pass filter. It is throwing away, it is perfectly, completely attenuating the components of the input at the frequencies above omega sub 0. And so it reshapes the spectrum. And then if we want to find out what happens when we transform this thing, when we go back to the continuous time world, now we're going to take this output, which has this as its DTFT, run it through a digital to analog converter, and we get something that looks like this. And so if we were to just look at these two, at least theoretically, it looks like we just went through some sort of continuous time low-pass filter, in this case an ideal filter. Now, in the real world, the A to D converters have finite number of bits and so forth. So, there are clues that this isn't really a continuous time system, inside. But, we can think about this box being pretty close to some sort of effective continuous time system. But what we're really doing is converting into discrete time, implementing with some discrete time system, and then converting back to continuous time. But this is what goes on inside, say, your phone or some other system that does this kind of thing all the time. Okay, moving on to the next slide here. So let's look at another example. So here's a very simple, low-quality, low-pass filter. So that ideal low-pass filter, as I said, we really can't build something like that. So one big thing we're going to address in this course is how do we design filters to get as close as we want to an ideal low-pass filter. We can't get perfect, but we'll explore how close can we get and what are the trade-offs, what are the pros and cons. So let's look at a simple filter. So here's the difference equation, and the first thing you notice is that there's only one term that involves the output. So we don't see any feedback terms, we see only feed forward. So if we go to our direct form type 2, we can draw the block diagram like this. Here I've used the symbol D to represent the delay. I could just as easily have used Z inverse for that, but here I chose to use D. And I've just I've structured the how I laid this out a little bit differently than the direct form, but it's basically exactly like the direct form type 2. And so this is our system. Another thing to notice is that what's really happening is each output sample is an average of the current sample plus the current input sample plus the most recent past input sample. So we add them together and we divide by 2 is effectively what we're doing. And since averaging is kind of a smoothing effect, we expect that this will suppress high frequencies, high frequency noises and things like that. So let's take a look at what this thing ends up looking like. We've got our generic difference equation, and we know how to get our generic frequency response from that. So if we apply that result to this difference equation, we can easily see how this works. Let me get rid of some of this stuff here so we can see. And yes, you're hearing my dog there, who's now left the room, but left the door wide open. Anyway, sorry about the dog barking. If we apply this idea to this, we get as our frequency response something that looks like that. So that's a very easy transition from difference equation to frequency response, and technically we can leave it like that. That's our complete general result for the frequency response. But if we want to see what this thing looks like, we could go to MATLAB and use FreakZ. But for this simple one, that seems like maybe a bit of overkill, and also this gives a nice scenario to just kind of, it's simple enough to explore by hand to see the mechanism by which this really works. So let's take that. So what we're going to do is just play a little trick. We see an e to the minus j omega, and we go, aha, Euler. So we can write that out as cosine of omega minus j sine of omega. And so, we went from something here that was in neither rectangular nor polar form, right? So we start off with something here that is the sum of two polar forms, essentially. And we've converted, the one is actually simultaneously rectangular form and polar form all at the same time. One of the few cases where it's both rectangular and polar. So we've converted the polar part into rectangular form, and now we can add the real parts together. So that's our real part, and here's our imaginary part. And so now to find the magnitude of this, we just apply our standard square root of the square of the real part plus the square of the imaginary part. And we have to include the 1/2 out in front as well. So if we do that, we get this. And then, so we're going to square this 1 plus cosine squared, and we'll get a cosine squared. We'll get a cosine, and we'll get a 1 out in front, 2 cosine and a 1 out in front. So these three terms come from squaring that. And then we add the sine squared part to that. And then what we're going to do is look at this and say, well, okay, I see something else going on here. I see a cosine squared plus a sine squared, and with a trig ID, I know that that is equal to 1. So now I get that 1 plus this 1 gives me a 2. Factoring that out, I get the square root of 2 out in front. Square root of 2 over 2 is 1 over square root of 2, and so I end up with something that looks like this. So that's an easy enough function that we can kind of work with and we can plot. So now we can plot that versus omega. Remember, we only need to plot from minus pi to pi. Everything outside of that will just be periodic replicas of that. So if we plot, we get something that looks like this. Roughly, I drew this by hand with PowerPoint, but it should look pretty close to this. So we see that we get a value of 1 near the low frequencies, and out at the high frequencies we are going down to have a 0. We know, looking at this, we can go back and say, aha, there is a 0 at on the z plane. There is a 0 right out here. There's the unit circle. There's a 0 right there at that plus and minus pi point, or z is equal to -1. So think about that. If it's not making sense to you, go back and review some of the previous notes. So we've got this, and we see that it is a low-pass filter, and it's passing some low frequencies and stopping or attenuating to some degree some of the high frequencies. And it's not a very good low-pass filter, and in fact we can find its cutoff frequency. If you remember, we defined cutoff frequency as where the magnitude squared drops to half, which means where the magnitude drops to 1 over square root of 2. So that would actually be right here. So it's a half band low-pass filter, but again, not a very good one. So how do we make better filters? Well, let's just play a simple trick right now and say, well, maybe if we average together more samples. So instead of adding together 2 and dividing by 2, let's add together n subsequent samples, input samples, and divide by n. I've written it this way so that we can see more clearly what the coefficients are for the difference equation, but we're effectively just saying the output at time n is equal to the average of the current sample plus the n minus 1 most recent past input samples. You average those together, and that's the output. And averaging is smoothing, and we're averaging more together, and we know that when we average more things together, we kind of get a better version of the average. So we should expect this to be, in some sense, a better low-pass filter. And on the next slide, I show this filter. We can find what its frequency response is. We can use freq z to compute what the frequency response of this thing looks like. Notice that I'm plotting this on a normalized discrete time frequency, so that -1 corresponds to -pi and 1 corresponds to pi. We can see that. And then what we can do here, I've done this for a bunch of different n values, and you can see that as the n value increases, we go from here to here to here to here to here, and so on. And so what we're seeing there is we're seeing more and more attenuation of the high frequencies. So we're seeing a narrower and narrower pass band and a better and better stop band. Although our pass band is still really not all that great. What we would really love to see is something that looks like this. Let me see if I can get rid of this stuff here and just kind of draw something in here. I'm going to go to maybe a different color. Let me go to a blue color, and let me go to something that's a little wider, just so that we can see this a little bit better. I mean, ideally, we would like a filter that kind of goes like this, more like an ideal low-pass filter. I'm only showing one side of this. We see that we're not really getting, even though we're getting a tighter low-pass filter, we're not really getting a better quality low-pass filter. And so what we'll need to explore in subsequent parts of this course, later in the course we'll talk about some very nice design techniques. But what we'll do is we'll see that there are ways to use filters like this, but instead of having all n terms weighted by the same coefficient, we will strive to find what are the best coefficients to put there to get us as close as possible for a given number of terms, for a given value of n. What are the best coefficients to pick to get as close as we can to a nice ideal low-pass filter? But nonetheless, we are seeing something here that by going to longer and longer, or larger number of coefficients, increasing n, that we do get the ability to, improve the filter in some way. And that aspect will remain. As we go learn how to do, very nice filters, we'll still see that once we fix n and find our best filter, if we let n get even bigger, we'll be able to find an even better filter. So that's why I say, you tell me how close to ideal you want to get, and I can get there. I just may need lots and lots of terms here. And notice that as I increase n, the amount of computation I have to do goes up. So that's a big trade-off too. So we'll explore these ideas more and more as we go into the course. There's a bunch of stuff that we'll go through first before we get into much of the filter design stuff, but we will get there. So here's another example. I already showed you how to use freq z, but here's another example of how to do that for a specific difference equation. This one does have feedback as well as feed forward. Here's the frequency response form, and then here are the commands that I use to plot that to create that and plot that. Now, here I'm using a command called linspace. Last time I showed you this freak z thing, we created our frequency vector by using the colon command. So we said like minus pi colon and then like 0.001 colon pi. So that's one way to do it. What this tells us is create a vector that starts at minus pi, goes to pi, and has 2,000 terms. In this one we're saying how many terms we want. In the other way we were saying explicitly what was the spacing. So in this form we have to think about what our spacing will be, and we can see explicitly how many terms we're going to get. In the colon form we see explicitly what our spacing is, and we kind of have to figure out what the number of terms is going to be. To be honest, I really care more about what my spacing is going to be, so I usually use the other form. Not sure why I used this form here, but other than to just illustrate that there are other ways to do this. So if we plot this particular one, we get something that looks like this. So now we're seeing something interesting here. We're seeing that we have a 0 here right at pi over 2. And in fact, if you look at this numerator, convert this back into the z form. Encourage you to do that. Replace, do our trick of z gets replaced by e to the j omega, but do it in reverse. E to the j omega gets replaced by z, so you should be able to go back, or equivalently start with the difference equation and go directly to h of z. Find the poles and zeros of this, and you'll find that you have a 0. If this is our let me see if I can fix that. Apparently I can't. So if we look at the pole 0 plot for this, here's our unit circle, we'll see that we have a 0 at plus and minus pi over 2. We'll also see that we have a pole fairly close to the unit circle at about pi over 4. So hopefully I won't totally obliterate here. So we'll have something that looks like that. And that should be it. That should be what we end up having in our system. So I would encourage you to do that little analysis. And that really shows how an engineer, signal processing engineer, simultaneously will use difference equations, z-transform, transfer function, pole 0 plots, frequency responses, plots of frequency responses, all simultaneously to think about what the system is doing and what kind of filter it will be. So we see here that we have a low-pass filter, but kind of an odd one, because we have this kind of little bit of resonance here at around pi over 4 and minus pi over 4. Maybe we want that. Maybe we don't want that. So if we're given the system and we decide, you know what, I don't want that there, we know how to fix that. You take those two poles, you don't want them as close to the unit circle as you have them. So take the z equivalent of the denominator, factor it into its factors with some number times e to the plus or minus j pi over 4, and then adjust that number out in front. Right now it's, I'm just making a guess. I don't really know. It might be sitting there at about 0.8 or something like that. And so change it to maybe be 0.3 or something. You'll see that you still have a low-pass nature, but that that resonant peak will go away. So I know we haven't really gotten much into MATLAB, but it's pretty easy to just fire up your MATLAB. You'll get one of these little double greater than signs as your prompt, you can go through these commands and literally compute this. Then try, reselecting these coefficients here to give you a pole that is same angle but farther from the unit circle, closer to the origin, and then see what that does for you. And you could even go one step farther and try to put a 0 out here to tack that down a little bit more. And you can start playing around with putting poles and zeros wherever you want, and seeing what impact they have. I really can't stress enough that doing that kind of stuff will really teach you how this stuff all works. All right, we got one slide left here, and this is just looking at another system where we've got a non-recursive filter with no feedback, and the generic form looks like this, and you can see that I've picked 3 coefficients. So I'm doing B0, B1, and B2 are 1, 2, and 1 respectively. And so I then compute the frequency response using freq z. I plot it, and we see the plot over here. And so now we're starting to see that by picking the coefficients other than being uniform, like we saw before, we're starting to shape this. Yeah, I end up with my passband being all the way up at 4, but we could fix that. We could find a way to scale this whole thing. Just put a 1/4 out in front of my B vector, and I've got that. The other thing that we can see here is that we've got a phase response that's perfectly linear. If you go back and look at the previous, the one with the feedback, our phase response was completely not a straight line. And if you remember, in Signals and Systems, we talked about ideal filters having linear phase. So this filter is not even close to ideal on the magnitude side of things, but on the phase side of things, it's got perfect linear phase. And there's a reason that this has linear phase, and we'll touch on this later in the course. I like to give a lot of spoilers early in the course, because typically students forget them anyway by the time we get to the real point. But then hopefully when you go back and you study for final exams, you'll come back and you'll go, oh yes, now I see. So I kind of leave these little breadcrumbs throughout the course, giving lots of feed forward and feedback, so to speak. I think that's a good way to teach. Anyway, we'll see later on that it's the symmetry. We see that it's 1, 2, 1. It's symmetric about the center coefficient. That symmetry will provide us with this linear phase. So this non-recursive form can always be made to have perfect linear phase as long as we choose our B coefficients to have this kind of symmetry. And so that's one of the advantages of this non-recursive filters, is that they can be made to have perfect linear phase. All right, I think enough foreshadowing there. We'll bring this set of notes to a close, and I will see you in the next set of notes.